Very good. So the next presentation is by Professor George Antoniou on the 4D Lattice IIR filter design. Partner.
Yes, hello. I welcome all of you to Athens. Me too. My presentation is about filters. EE. Okay, the first part, 0. We're going to see about a review. What is this? And the required background for that. So I'm going to talk about the conventional 2D basics, talk about state space models for conventional and 2D. All this can be extended to more dimensions. Like I'll explain to you why this is very important. Now, the part 1, I'm going to talk about 2D. This way you can see the results from the beginning. And after this, I'm going to talk about 4D. Now, to go from 1D to 2D, it is not an easy task. The same way to go from 2 to 3, it is not an easy task, and so on. And finally, talk about the conclusions. Okay, 1D, 2D, basic knowledge. 1D, example. Okay, function of one variable, 2x plus 1. This function has a root, correct? Also, this is the quadratic. This is 2 roots from high school. Therefore, 1D, it is voice, the conventional signal. 2D dimensions. 2D, 1, 2x plus 3y plus xy. 2 dimensions, okay? 2 variables, 1x, 1y. Also this is another function, 2 dimensions. What is a 2-dimensional system? It is an image. Okay, fundamental. Okay, it is known from Gauss that 1D polynomial of degree n can be factored into product of n polynomials of degree 1. So therefore, we can find roots. But for 1D polynomials, finding the factors, it is equivalent to find the roots of the polynomial. Example. For this, it is counting to find the roots easily. It is 1, 2, I'm sorry. For this, it is 1, 2, 3, and 3, double. But there is a fundamental theorem of algebra for 2D, 3D, 4D, and so on. So 2D are the applications for images. Very important. Okay, so 2D and ND cannot be factored. So therefore, there is no roots. Now what? Only you can factor for special cases, not in the general case. So therefore, we don't know if it's a special case or not. Okay, so for example, this 2x, 2y plus 6. And this is 4x, 3y plus 12. Those have roots, but those actually are not 2D polynomials, are 1D polynomials. Because this is x plus 2, y plus 3 are 1D. So therefore, we can apply what we know. The absence of the fundamental theory of algebra, it is very significant. Why? Because not all known 1D algorithms, methods, and techniques can be applied to 2D, 3D, 4D, and so on, ND polynomials. Therefore, we have to propose new theorems, new algebra, new mathematics, which is not visible, okay? It is invisible. So algorithms, and methods, and techniques for 1D minimum state space realization cannot be used for 1D and MD system and filters. Review. 1D state space systems. What is this? This comes for control systems. AA. Okay, we have 1D state space, conventional, analog. We have 1D state space, digital. Okay, the continuous 1D, it is this, where the U is the input, Y is the output, and this is the state. This is what we learn in linear systems. So this is the analog, and this is the digital. Now, I plus 1, A, X, I, this is the U is the input, the Y is the output. We apply the Z transform, the conventional 1D, and we find, okay, the numerator and the denominator of the filter. 2D. Now, we have 3 models. One that is the Bonnie-Roser, and I'm going to introduce a new modified one for my filter. Okay. So therefore, the first one was introduced in IEEE transactions on computers, and this has 1 plus 1, J plus 1, which means vertical and horizontal, okay, an image. And this is the input, and this is the output. So therefore, we can make a condensed form of the model. So therefore, this is the horizontal, and this is the vertical, on the top and bottom. This is the initial model, okay, and the matrices. So this is the Bonnie-Roser, the classical 2D space model. Okay, now, again, the same thing, we can apply the 2D transform, and this is, again, the transfer function for the Z. It is all the Z's on the top, Z1, Z2 on the bottom. Okay, my model, it is a little bit different. The same idea, like the Roser, but the variables are x1, h, x1v, x1a, x1v. So therefore, it is something that interchanges. And why this? Because it allows me to generalize my result. And again, applying the 2D Z transform, but in this case, the diagonal is Z1, Z2, Z1, Z2. This is in 2D case. In a 4D case, this is Z, Z1, Z2, Z3, Z4, Z1, Z2, Z3, Z4, and so on. 4D filter. Okay. I carry work today. I'm going to introduce a mixed lattice IIR filter, which means it has the numerator and denominator. And why I talk about minimal? Because it is not only because of the hardware requirements, but non-minimal realization cause theoretical and also computational difficulties. Okay, so therefore, minimal are not always possible even for 2D. So therefore, I talk about 4Ds, and always the dimension of the state vector it is minimal. Also, the circuit, it is minimal delay elements. Okay, so therefore, I will talk about only first order 4D, which means 4 by 4. A 2D, 2 by 2. Okay, 2D port. So therefore, this is an 1D. Okay, 1D lattice, conventional, because you can see the arrows go left and left, left and left. Okay, this is what we learn in linear system. This is the basic lattice 1D filter. Okay, now, there is also another one, which is not in the textbooks. Okay, so therefore you can see I have this to be a right, and a right variable. So therefore this is a different structure, but has the same transfer function. 1D port. For this 1D, we can also have a mix where the left, it is left and left, right and right. So therefore, this is what I extend to for this. And this is what we know. The top, it is the left convention. This is the right, or inverted. And this is the mix. The mix goes left and right. Therefore, this is the mix 2D. We write the equations, okay, by inspection. We derive the minimal state space model 2 by 2. And also at the end, if we apply the Z transform, we can find the numerator and the denominator. We can see that this is correct. The numerator and the denominator are mirror images. Delta 1, delta 1, delta 2, delta 2, and 1. We have all for this way. Also, another way you can see around is this. Okay, so therefore, the blue, the green, and the red, which means the 2D preserves the 1D conventional property. Okay, now this is 4D, mixed. This is my filter, okay? This is my new result. Okay, in this case, it is mixed on the left, it is mixed on the right. So this is a left, right structure. Again, I extract the equations from the circuit. It is minimal, and this is, you can see, HDD, HDD is order 1. This is 4 by 4, which is minimal, the state space. And also, we can see this is a transfer function, the reflective structure. You can see this is the gray code, C3 and C4. They have the same coefficient. And for the audience, I made another way using binary numbers. You can see the numerator, the denominator. You can see at the top, as I progress, the blue, the red, the green, the same, the blue, the red, the green, the blue. Delta 2 is the same. Also, the other way around, it's symmetrical. I can go up and down, so therefore, you can see that this is a mirror image of the numerator and the denominator. So therefore, the 1D structure, okay, applies to 4Ds. And this is also another structure that I have. You can see the left and the right, also the top and the bottom. So therefore, the top and the bottom, the red, it is the same. You can see it. 1, delta 4, 3, 4, 3, 2, 3, 2, 4, and 2. Also the other way around. Delta 1, 1, 4, 1, 2, 3. So therefore, this is also a correct transfer function for the given 4D filter. And finally, okay, this is another form. You can see, okay, up and down that the coefficients are equivalent for the numerator and denominator in a mirror image structure. This is also, I didn't analyze the results because this is only order 1. So this is the state space, the realized state space matrices for N, where A, B, C, and D are the derived matrices. And then in this study, a new 4D lattice all-pass filter having mixed right and left directions has been presented. The proposed 4D circuit uses a minimal number of delay elements. The dimension also of the state vector is minimal, and the resulting 4D transfer function exhibits the well-known 1D all-pass mirror image lattice characteristics. Okay, now, what is so important about this? Using the multidimensional framework, you can redesign high-order 1D filters, which is not possible. Up to now, everybody uses 1, 2 the most, 3 the most. They don't use 4th and 5th order 1D filters. Using this technique, you go from behind, okay? You derive the 4D, 5D transfer function, and then by making Z2, Z3, Z4 equal to 1, you can go back to 1D, and then you can increase the size of the filter using the transfer function. The only drawback, it is you have to invert matrices that have characters, which is very important, okay? And you must write specialized program in Java or Python. Okay, thank you for your attention. Questions?
Very sound question. Is application on your method on 4D?
Okay.
With,
Normally,
with
1D, 1D, it is the voice. 2D, it is an image. 3D, it is a movie. 4D, virtual reality. It is 3-dimensional one.
virtual reality.
Okay? This is mathematically, it is possible. Okay? In a human beings, we don't see the 4 dimensions.
Science, I mean, the application.
But you can write programs, okay, to do all this.
And the time of processing?
The time processing, for now, a 5D, a 6D crashes. Okay? Up to 5D, it is okay. 5 years ago, we could do only up to 4Ds. Today, you can do 5Ds, 6Ds, only the denominator. IIR, only 5Ds. Can work for 2 days and no result. Questions? Thank you.
Thank you.